Now that we know how to prove triangles are similar, we can talk about some properties of similar triangles. So I just want to highlight this so we all are on the same page here. We're dealing with similar triangles. So we need to know triangles are similar before any of these theorems and properties work. So first we're going to talk about our triangle proportionality theorem. So this theorem says if a line of parallel to a side of a triangle intersects the other two sides, then it divides those sides proportionally. So this can be a line that cuts through the triangle, right? Like example one below. Let's take a look at what this looks like in a diagram and see what we can conclude with our given information. So this is what our triangle could look like. You see triangle ABC and this line EF that cuts through it and is parallel to one of the bases. That's basically what you're given. So you can be given the line EF or just the segment EF that would start at E and end at F. Okay, so if this is true, what can we conclude? We can conclude that the pieces of the entire side of the triangle are proportional. So BE over EA is going to equal BF over FC. All right. And you can see that we do create two similar triangles out of that. So we can see how the pieces of the sides are now proportional. So let's take a look at example one and try this out. So if I want to find CY, this is the value I'm looking for. Remember, you can put in variables if you want to tell you what you're looking for. I'm going to call this X, right? And then I want to set this up. Well, first, you want to see, are these triangles similar? They should be for me to use this problem, for me to use this theorem. And yes, they are, because we've got reflexive A, and I've got corresponding angles that are congruent. So that's awesome. So now how would I set up the proportion using my theorem? Well, remember, the piece in the middle, this XY, that's splitting this larger triangle ABC into two pieces, also splits the sides proportionally. So I would know that BX over XA is equal to CY over YA, right? And then I can just solve the proportion. So 4 over 9. Notice I'm not adding 4 plus 9 here because I'm not comparing the whole side to one part. I want to go part to part. Okay, so 4 over 9 is equal to x over 10. And then you guys know how to cross multiply and solve. So feel free to leave your answer as a fraction. So I'm going to get 40 over 9. All right. You guys go ahead and try that try problem. Go ahead and find that US for me. So did you get 7 over 2 or 3.5? That's what we want to do. One thing I want to note, this 4 over 16, I went with it the way it is, but you could have also reduced this 4 over 16 to 1 over 4 to make your life a little bit easier with your math work. All right, so that's our first theorem. Now we can also talk about the converse of the triangle proportionality theorem. And if you remember, we've had converses before. And one of the big chapters that dealt with converse theorems was chapter 3, where we talked about the converse of the alternate interior angles theorem, the converse of the corresponding angles postulate, and all that. So this converse theorem is also going to help us prove lines or segments are parallel. So you can see this really is just the converse of that first theorem. So if a line divides two sides of a triangle proportionally, and that could be a line or a line segment, then that line is parallel to the third side. So let's see how this changes what we're given and what we can conclude. So you'll see how the diagram is still very similar. It's pretty much the same thing. You've got a triangle, this large triangle in blue, and a line or line segment that's in red here cutting across two of those legs. The difference is I don't know DE is parallel to AC, but what I would know here is that the pieces would be proportional. For example, BD over DA would end up being the same ratio as EB over EC, right? So if we see that happens, then we can say that DE is parallel to AC. All right, so a big clue of when you're going to be using this is when you see example 2 type problems where you're asked to verify that one side of the triangle, this KL, is parallel to a side or a segment intersecting two of the sides of that larger triangle. So if I want to verify these are parallel, what I want to do is I want to work with the proportion. And again, just a side note here, notice these triangles are still similar. We've got reflexive J and we've got proportional sides. So 30 over 45 would equal 42 over 63. So just keeping that in mind, these are all similar triangles. Now, how would I check if MN is parallel to KL? Well, then I'm going to check that the pieces of those sides that are being cut are proportional. So I'd be looking at JM over MK, so those two pieces. I want to see, is that going to be congruent to or equal to JN over NL? Plug in your numbers and let's check. So 42 over 21, is that going to equal 30 over 15? Yeah, because they both reduce down to 2 over 1, right? So we would say since JM is over MK is equal to JN over NL, MN is indeed parallel to KL. All right, go ahead and try that U-try problem and tell me what you think here. So once again, you're checking the pieces, right? AD over DB. Would that end up equaling AE over EC? Well, 16 over 15 doesn't reduce any farther, but 8 over 12 gives us 2 over 3, and those are clearly not the same. So no, we don't have our parallel segments here. All right. Moving on to transversal proportionality corollary. So that gives us a clue. We're looking at two transversals, meaning we're going to be looking at two lines now cutting through our triangle. Let's see what this says. So this corollary tells us if three or more parallel lines intersect two transversals, remember the transversals are the lines that intersect the parallel lines, right? They are normally the slanted lines in our pictures. Then they divide the transversals proportionally. And this is a corollary because your two transversals are going to eventually make a triangle. So let's take a look at what this looks like. So this picture would be what you're given. Notice the three parallel blue lines, those additional arrows indicate parallel. And I've got these two red transversals cutting across all three of those lines. And again, I could have 4 blue lines, 5 blue lines, it doesn't matter. It's 3 or more. So if this happens, what we know is that each of these little pieces between the parallel lines are going to be proportional. All right, so that means AC over CE would be equal to that ratio BD over DF. Take a look at example 3, and let's find the missing value, that question mark. And remember, you can always use X to indicate what you're trying to find here. So how would I set up my proportion? Well, remember, I could be comparing the pieces of the sides, right? Keeping this top with the top, the bottom with the bottom. So I would say 15. Oops, let me make that a little clearer. So 15 over 6, that should equal that larger piece, 25 over x. And then I can cross multiply and solve, like I'm sure you're all pretty used to now with your proportions. So 15x equals 150, and we're going to get x equals 10. Go ahead and try that U-try problem, and let's see what we get for that question mark, that x value there. So hopefully you guys got x equals 14. Check your setup, right? We can go x over 28 equals 8 over 16. Of course, you could have also flipped it. You could have done 28 over x is equal to 16 over 8. And notice this time I decided to reduce that fraction because it makes my multiplication a lot easier. So I reduced that to 1/2 and then cross multiply, get x equals 14. All right. Last theorem. Now we're going to move away from sides and let's talk about the triangle angle bisector theorem. So this theorem says that an angle bisector of a triangle divides the opposite side into two segments whose lengths are proportional to the lengths of the other two sides. And I think the words are really confusing, so the diagram is going to really help us understand this. Okay, so this would be a diagram you'd see. So you'd see an overall triangle in blue, ABC, and some bisector, this ray right here, BD, that comes out of one of the vertices and then hits the opposite side. So when you're setting up your proportion, what you're going to do is you are going to be looking at the two pieces of the side opposite of that bisector. So in this case, we'd be looking at AD and DC. And we're going to go ahead and set that up as our first ratio. So AD over DC, right? And just to be clear, let me just highlight these pieces so you can see how to put them all together. All right. And what we're going to do is we're going to compare that to the two remaining sides AB and BC. And you might be wondering, well, which one goes on top? Well, what you're going to look at is you're going to look at the side that connects to that bottom piece. So for example, this AD in yellow is connected to this AB side. So that means I'm going to put AB on top because that's where AD is. So again, see how that AD and AB create that half of the triangle there that looks like half of that corner? So we're going to put the two yellow pieces on top, which means the remaining side, this BC, see how it connects to DC down here? Well, that means BC is going to go on the bottom because DC is on the bottom. And that's how I write my proportion. So this one is one I definitely see a lot of people kind of get confused on because you're not sure how to set up the proportion. So again, if it helps, highlight, draw, mark up your diagrams, okay? We're going to do one final example and you're going to try one more and that'll be it for this video. So when you're looking at example 4, we want to think, okay, how do I find RV and VT? Right? How do I set up this proportion? Well, think about what that theorem said earlier. We're going to put the two pieces of the side that's opposite of that angle that's being cut in half, right? So that's going to be RV and VT. So let's set up our first ratio, so RV over VT. And then we want to think, well, what should it be paired up with? Remember, you want to keep the sides kind of in the same position. So this 10 connects us to x plus 2, so I'm going to put a 10 on top, right? So that's going to be the SR. That 10 was SR, right? And then what do I put on the bottom? Well, that's going to be the piece down here, this 14, this ST, that connects to that 2x plus 1. So I get RV over VT is equal to SR over ST. Okay, and then go ahead and substitute in your value. So I'm going to get x plus 2 over 2x plus 1 is equal to 10 over 14. All right, and then I'm just going to move this up so I have some space to work. Then you're going to go ahead and cross multiply and solve. And again, you can simplify if you want. I'm going to simplify because I like to work with smaller numbers. I can divide both 10 and 14 by 2 to get 5 over 7. And then use your parentheses to cross multiply. So I'm going to get 7 times x plus 2 is equal to 5 times 2x plus 1. Distribute. And then we're going to solve that equation. And I'll save you some time and do the rest of it. So we got x equals 3. And then remember, that's not what I'm looking for, though. I'm looking for RV and VT, so plug it in. RV is going to equal 3 plus 2, which is 5, and VT is 2 times 3 plus 1, which will be 7. And here's my answer right over here. Okay? Go ahead and try the you-try problem, being very careful with how you set up your proportion. And hopefully you got these answers. X equals 30, PS is 28, and SR is 35. We'll be practicing this in class. Please come back with questions. And thanks for listening.